Both of these interactions are non-local from our perspective. Reality emerges from in between these two interactions. We seem to only be able to interact with entangled particles strongly through strong decoherence. We're only interacting with the unwinding particle on the left every time. Our detectors are localizing particles non-locally. They are interacting non-locally. We know that the Higgs is what gives particles mass. So what if the Higgs mechanism is non-locally interacting with this entanglement system, creating our local fermions that we are familiar with? Our reality emerges from these non-local boundary interactions. Here we have a crude simulation of wave function collapse. A wave is simply a string that has zero tension. The coil is very loose. A particle has high tension. It's the same object but localized. When we interact with particles and localize them, this is what we are seeing, figuratively. By randomly interacting with one of the rings of the coil, the rest of the quote-unquote particle will localize around that point. The internal angular momentum will complete this interaction, creating a localized particle. It looks random, but we are just selecting a location on one of these rings. The more spread out this coil-like, wave-like object is, the more random locations there are to choose from. If I were the Higgs mechanism and this was an electron, this would be completing the other half of the entangled interaction. If the Higgs mechanism strongly interacts with the winding particle, it'll create immense curvature and warping, analogous to a black hole. The angular momentum of the entangled particles at the event horizon of a black hole has completely stopped at this point. This is analogous to extreme time dilation for observers outside the event horizon of a black hole. Because this string is mechanical, it has directionality. Graphically, light is represented at a 45-degree angle in special relativity to show the relationship between space and time. This mechanical string seems to represent both quantum mechanics and general relativity at the same time in one underlying object, just looked at from a different mechanical perspective. This is a bottom-up approach for gravitizing the quantum.